In this video, I am going to discuss with you about circular motion. What is circular motion? When do you call the body is moving in a circular motion? See, the name itself defines it. The body is said to be in circular motion if it is moving in a circular path. The body is said to be in circular motion. The body is said to be in circular motion if it moves in a circular path, right? That's so simple definition. The body moving in a circular path is called, we say it is moving in a circular motion. Suppose this is your say circle having say radius r and say center at O. This can be your radius, alright. So say R. So if the body is moving in this circular path, we say it is in circular motion. In circular motion. Now circular motion also we can have two kinds: a uniform circular motion and non-uniform circular motion. Suppose the body is over here. See, body is at point P. Then of course its velocity, I told you earlier also, the velocity is always tangential to the path. This is the path. So if the body is at point P, its velocity will be lying in this direction. This velocity is going to lie in this direction. I can take this as O, the center can be taken as origin, and I can take this as initial line. So this will be R. So if the body is lying at point P, this is theta suppose, right? So V will be tangential to the point, tangential to the circle, right? Now based on whether, so one thing is very clear before I go to that. One thing is very clear: as the body moves, its velocity keeps on changing. Velocity, direction of velocity keeps on changing. If the body is here, the velocity is in this direction. If the body is here, the velocity is in this direction. The body is here, the velocity is in this direction. So as the body moves in circular motion, so velocity always keeps on changing. Why? Because direction keeps on changing. What about magnitude? Magnitude may be constant, may not be constant. If magnitude of velocity is constant, see, direction will always change, of course, but if magnitude of velocity is constant, if magnitude of velocity is constant, that is, let's write V, then we call it uniform circular motion. In that case, we call it uniform circular motion. Then it's called uniform circular motion. It's called uniform circular motion. Get your point? Is it alright? So if V is the speed, if the speed of the particle remain constant, then we call it uniform circular motion. And if speed changes with time, then it is a non-uniform circular motion. Then in that case, it is a non-uniform circular motion. If speed does not change with time, it's called uniform circular motion. And if speed changes with time, then it is called non-uniform circular motion. So first of all, let us discuss what is uniform circular motion. Let's discuss about uniform circular motion. So here what do you have? The magnitude of velocity, which is V, is remaining constant. And one more thing, in circular motion you can see that if it is circular motion, what is quite obvious thing? The quite obvious thing is this R, distance of point P from the center, will not change with time. That remains fixed. Distance of point P from O does not change with time. Does not change with time. So R is constant in circular motion. The distance of point P from the origin I have taken the center as, I have taken center as the origin, so I can say the coordinates, if I assign coordinates over here r and theta, if suppose point P is here, so I can assign coordinate r and theta. So you can say r coordinate is unchanged, theta keeps on changing, but r does not change, right? So in that case, in general, in the last video we have discussed, if velocity in a plane polar coordinate system, if I take it an initial line and this is the origin, the velocity is given by what? R dot er and r theta dot e theta. So this will be 0, and velocity has got only transverse component. See, for this we don't need to apply this formula. If somebody say it is circular motion, then one quite obvious thing is velocity is always tangential to the path, and tangent to circle is perpendicular to radius. Tangent to circle is perpendicular to radius. So in that case, velocity is tangent to circular motion. So velocity is perpendicular to radius. So it is perpendicular to radius means it does not have a radial component. If velocity is perpendicular to radius means it does not have any radial component. So velocity is only transverse. Velocity is purely transverse in nature. Velocity is purely transverse in nature, right? And this is the speed. Speed is r theta dot, which is v, and theta dot is called angular velocity. We call this theta dot as angular velocity, right? So omega can be written as v by r. In circular motion, omega, the angular velocity, the rate at which theta changes, it is v by r. So v is the speed of the particle in circular motion. It is speed of the particle in circular motion. Alright, getting a point? Okay. So what we have learned till now, if a body is moving in a circular motion, the velocity keeps on changing. Why? Because direction keeps on changing. So circular motion is always accelerated motion. In a way I can say circular motion is always an accelerated motion, because when the velocity keeps on changing direction, then velocity keeps on changing. See, a vector is said to be changing. Vector is supposed to change if its direction changes or magnitude changes. So here what we are finding that the direction always keeps on changing. So it is an accelerated motion. Velocity keeps on changing its direction. So velocity change means it is undergoing acceleration. Regarding magnitude of velocity, magnitude can change, magnitude may not change. If magnitude of velocity does not change, you call it uniform circular motion. If magnitude of velocity does not change, you call it uniform circular motion. Okay? Getting a point? Okay. So once we have understood that circular motion is accelerated motion, so we'll be definitely interested in finding acceleration. Once we are saying that circular motion is accelerated motion, so we'll be definitely interested in finding out what? Your accelerations. What could be acceleration? See, what is velocity? Velocity is what? V e theta. V is the magnitude of velocity, and it lies in direction of e theta always. See, this is er, and this is e theta. So velocity perpendicular to r, so it's lying in direction of e theta. And if I find acceleration, so acceleration is what? D by dt of v, or this is d by dt of v e theta. And since we are talking about uniform circular motion, so dv by dt would be 0. So this is going to be 0 if it is uniform circular motion. So what is d e theta by dt? We have just found. What was d e theta by dt? We have just found here. See, this is d e theta by dt. So put it over here. Theta dot er. Theta by dt is theta dot er. So this will be v minus theta dot er. Or theta dot is what? V by r. We can write v square by r. We can write it here. V square bar ER, or V can be written as R theta dot, or minus, and this case omega, so you can write minus. So what is saying? It's saying that when the body is undergoing uniform circular motion, its velocity keep on changing its direction, and acceleration is this, or we can say acceleration is, if I write V as omega r, is this. This is the acceleration. So what do you find? When the body is moving in a circular motion, it is in fact accelerating in radially inward direction. It is accelerating in radially inward direction. And this is called, this acceleration, the magnitude of this acceleration, or this acceleration simply, that's called centripetal acceleration. Centripetal means towards center. Since it is radially inward direction, so it is towards center. So that's called centripetal acceleration. So when the body moves in a circular path, if it undergoes a uniform circular motion, its acceleration is towards center, and we call it centripetal acceleration. That centripetal acceleration is V square by R. That centripetal acceleration is V square by R. Right? There are other ways of proving it also. There are other ways of proving it also. Should I discuss those ways? That will be more, that will involve more physics and less mathematics. So should I tell you how it is radially inward? Let me try. If you understand, it's good. If you don't understand, then also it's good. You must know this. You must remember this fact, that if a body is moving in a circular motion, then its velocity keep on changing its direction, and its acceleration lies in radially inward direction. Its acceleration lies in radially inward direction, and that acceleration is V square by R or omega square by R in radially inward direction. Why radially inward? ER is unit vector in direction of increasing R, and you have minus sign over here. So that means this acceleration is radially inward. This acceleration is radially inward. Now we will try to visualize this, how it is in radially inward direction. Right? Let me tell you this. Now let's try to see the whole thing geometrically also. I'll take another page. So suppose this is circular motion which the body is moving. Right? This is circular motion. This is the origin. Let's take. Suppose at time t, the body is here. Say this is your V vector at time t. This is theta. This is Vt. Yeah. At time t plus dt, this is the position at time t. Suppose at time t plus dt, the body moves here. At time t plus dt, the body moves to this position. Get your point? Body is here. This is your V t plus dt. This is Vt, this is V t plus dt. And suppose this angle is d theta. This angle is d theta. So I am interested in finding out the change in velocities. Change in velocity is what? Minus Vt. So how will you get this? You just join the tail of Vt and Vt plus dt. So how will you join tail? You have to move parallel to itself. So this can be your Vt, and this vector is Vt, this final vector is initial vector, and this is going to be our, let me use another pen over here. So this is going to be our, this black one, this vector is going to be a delta V, or say dV, the change. And what's the direction of dV? It's in radially inward direction. You can see this is direction of dV. That means since dV lies radially inward direction, the acceleration will also be radially inward. But to say that it is radially inward, just drawing is not enough. See, that's so the success of my drawing. In fact, just showing like this, and we have to prove that this dV when extended passes through center. That's what we have to prove actually. We have to prove that dV when extended passes through center, right? And that is quite obvious. See how? See, in uniform circular motion, the magnitude of Vt is constant, and I have already showed that if the velocity, if the vector has got a constant magnitude, then its derivative is perpendicular to vector. Then its derivative is perpendicular to v. We have already shown this. Do you remember? Here I have shown you this thing. Here, see. This derivation was there. I have deleted it. So I have already shown that if vector has got a constant magnitude, its derivative will be perpendicular to vector. See, if v has got a constant magnitude, du by dt will be perpendicular to v, and v is tangential. So perpendicular to tangent is radial. Perpendicular to tangent is radial. So it is in radially inward direction. It is in radially inward direction, right? And we can find the magnitude of dV also. See, if this is d theta, this would also be d theta. Get your point? And I can get the magnitude of dV. See how? This is Vt plus dt. This is your and this is your dV. Right? This is your dV. This is V T. I've just put this, magnifying this. I'm just magnifying this part. And here you have Vt, and here you have d theta. I've already proved this, that dV by dt is lying in radially inward direction. So now I have to just show the magnitude. See, this dV is, the magnitude of dV is what? You know cosine rule? I think you are aware of cosine rule. This is theta. So A, B and C. C square is A square plus B square minus 2AB cos theta. So we can use this. dV square is square minus yes minus yes minus into cos d theta, and the magnitude of velocity is not changing with time. So this is v square, so dv square v square plus v square minus 2v square cos d theta, or 2v square cos d theta, or this is 4v square sin square d theta by 2, or dv is 2v and d theta is very small, so sin d theta by 2 is d theta by 2. So It is v d theta, and dv by dt is going to be, which is acceleration, is v theta by dt, which is v theta dot or v omega, or this can be v square r or omega square r. So when the body moves in circular motion, it undergoes an acceleration radially in one direction with this acceleration, this acceleration. That's the other way of getting it. That's the other way of getting it. Okay, getting a point? That's the other way we can get this acceleration. You can visualize it like this. So now it is settled fact that if a body is moving in a uniform circular motion, then its acceleration lies in radially inward direction. Its acceleration lies in radially inward direction. And what about non-uniform acceleration? See, if it is non-uniform acceleration, we can't say this. See how? If it is non-uniform acceleration, sorry, non-uniform, no, not non-uniform acceleration, non-uniform circular motion. I should not say non-uniform acceleration, I should say non-uniform circular motion. If it is non-uniform circular motion, if it is non-uniform circular motion, in non-uniform circular motion, what do you have? The magnitude of velocity is not constant. In that case, your direction of velocity will always be transverse. But now acceleration, if I find, see, I made this 0, but now I can't make it 0. This will be dv by dt e theta and v. So you have what? V dot e theta minus, so in that case you'll have acceleration in radially inward direction and also transverse acceleration. You'll have a acceleration v square in radially inward direction, and depending on whether v dot is positive or negative, it will have acceleration in direction of e theta or opposite to e theta. We don't know whether v is falling or increasing. If v is increasing in magnitude, in that case the transverse acceleration will be in this direction. If v is falling in magnitude, then transverse acceleration will be in this direction. And the sum of these two accelerations, this is transverse acceleration, this is radial acceleration. The net acceleration would be something like this. So in that case, the acceleration, net acceleration will not be radially inward. It's only in uniform circular motion that net acceleration lies in radially inward direction. So you must make note of this. In case of uniform circular motion, this part becomes 0 and hence acceleration always in radially inward direction. Whereas in non-uniform acceleration, your non-uniform circular motion, where the velocity, the magnitude of velocity is not constant, the acceleration is not in radially inward direction. I hope you understand. So I'll stop over here and continue with the other topics in next lecture. Okay, thank you very much.